Look at the reality of modern enterprise networks. There is no physical perimeter. Data flows constantly through a vast, uncontained environment, routed over hardware you do not own and across borders you do not control. By default, every packet is exposed. To enforce security in this state of continuous exposure, security architecture relies on an abstract concept known as the reference monitor. This is an access control mechanism that must mediate all interactions between subjects and objects. To function, it has to be invoked on every transaction, small enough to be rigorously tested and entirely tamper-proof. In digital communication, the mechanism that provides these guarantees is cryptography. Modern cryptographic engineering operates on Kerckhoffs' principle. The premise is straightforward. A crypto system should remain secure even if an attacker possesses the exact schematics of the algorithm. You never rely on hiding the mathematics. The entire security burden rests solely on the management and protection of the cryptographic keys. This creates an immediate architectural tension. Protecting massive volumes of data requires algorithms that operate with microsecond efficiency. But verifying the identities of millions of users requires a complex, mathematically intensive system of key distribution. You cannot achieve both with a single algorithm. Modern security architecture is built on a specific synthesis, combining the raw computational speed of symmetric engines, the infinite scalability of asymmetric trapdoors, and the strict governance of public key infrastructure. The engine driving bulk data protection is symmetric cryptography. Algorithms like AES and ChaCha20 utilize a single shared secret key to both encrypt plaintext and restore the resulting ciphertext. This diagram illustrates exactly why symmetric algorithms are chosen for heavy lifting. They are designed around substitution permutation networks, which rely heavily on bitwise operations and logical XORs. These mathematical processes are highly amenable to hardware optimization, directly mapping to dedicated CPU instructions like the AES-NI set. Because the math is executed directly at the silicon level, these operations complete in microseconds. That makes symmetric encryption approximately 1,000 times faster than asymmetric alternatives. Engineers deploy this speed in two distinct ways. Block ciphers like AES process data in fixed 128-bit chunks, making them ideal for securing data at rest in databases. Stream ciphers like ChaCha20 process data bit by bit, prioritizing the low-latency processing required for real-time voice-over IP and streaming video. But symmetric systems possess a severe operational flaw, the key distribution paradox. To share a secret key securely, you must already have a secure channel. But you cannot establish that channel until you have shared the key. This graph demonstrates the mathematical reality of key distribution in open networks. Every unique pair of communicating entities requires a distinct shared key to maintain confidentiality. The formula governing this growth is n times n-1 divided by 2. Plug the numbers in. An organizational network with just 1,000 users would require the secure generation, distribution, and storage of 499,500 unique keys. Symmetric encryption provides a computationally perfect engine for securing bulk data, but it mathematically and logistically fails to scale across open networks. The solution to the scaling problem requires a shift in mathematical approach, asymmetric or public key cryptography. This system decouples the process by giving each entity a mathematically related key pair. The public key is distributed openly for encryption, while the private key is held strictly secret for decryption. This dual key mechanism means two parties who have never interacted before can securely communicate over a hostile network. The symmetric key distribution crisis is solved. The security of this mechanism relies entirely on trapdoor one-way functions. These are mathematical operations that are trivial for a computer to execute in one direction, but practically impossible to reverse without possessing the specific trapdoor information contained in the private key. Looking at this comparison, we see the evolution of the trapdoor. On the left is the traditional method. Algorithms like RSA rely on the difficulty of factoring the product of two very large prime numbers. On the right is the modern architectural standard, which uses the algebraic structure of elliptic curves. The math on the right relies on the elliptic curve discrete logarithm problem. Attempting to reverse scalar multiplication along this curve is exponentially harder for a computer to solve than brute forcing the integer factorization used in legacy RSA. Because the math is harder, the keys can be smaller. An elliptic curve key at 256 bits provides the exact same cryptographic strength as a massive 3072-bit RSA key. This 12-fold reduction in key size dictates modern hardware design. Smaller keys require drastically less power to transmit and less computational overhead to process, making ECC the only viable public key option for mobile applications and the Internet of Things. Asymmetric math also enables digital signatures. By encrypting a message digest with their private key, a sender provides proof of origin. This allows any relying party with the corresponding public key to verify the integrity of the data and the identity of the sender. Asymmetric cryptography perfectly solves identity verification and key distribution. However, the complex mathematics require milliseconds to compute per transaction. If you encrypt a gigabyte of data asymmetrically, the system will grind to a halt. We are left with two halves of a solution. Symmetric engines are fast but unscalable. Asymmetric trapdoors scale but are mathematically too slow for bulk processing. This timeline illustrates the definitive architectural compromise, hybrid cryptography. It is perfectly demonstrated by the TLS 1.3 protocol. A secure connection is split into two distinct operational phases. In the first phase, the systems utilize asymmetric cryptography, like RSA or ECC, strictly to authenticate the server's identity. Once verified, they use that asymmetric connection to securely exchange a randomly generated temporary session key. The instant both machines have that shared session key, the asymmetric operation is completely abandoned. The architecture pivots entirely to hardware-accelerated AES algorithms for the high-speed transfer of data. By isolating the heavy mathematics to the initial handshake and delegating the data payload to silicon-optimized ciphers, engineers effectively eliminate the weaknesses of both algorithms. This millisecond synthesis makes global digital commerce possible. A mathematically unbreakable key is useless if you cannot verify who actually owns it. If an attacker presents their own public key while posing as a trusted server, the encryption works perfectly, but the data is delivered directly to the adversary. To establish objective trust, architects deploy a public key infrastructure. At the core of a PKI is the certificate authority, a trusted entity that officially binds verified identities to mathematical keys using digital certificates. This tree diagram maps the required hierarchical chain of trust. At the top is the root CA, which signs the certificates below it. Because the root CA is the foundation of trust, it is typically kept completely offline and physically air-gapped. Day-to-day issuance is handled by subordinate intermediate CAs. This topology is an intentional containment strategy. If a server is compromised, engineers can surgically revoke an intermediate CA without needing to regenerate the foundational root CA, which is already permanently installed on millions of devices worldwide. This brings us back to Kerckhoffs' principle. The algorithms are public. The ultimate center of gravity in any security architecture is how securely you manage the physical lifecycle of the keys themselves. The lifecycle begins with key generation. It is not enough to run a software script. Keys must be generated using true entropy within cryptographically strong, tamper-resistant hardware environments. This matrix compares the two primary hardware approaches. For local endpoints, a trusted platform module, a dedicated chip on the motherboard, securely holds the system's local keys. For centralized enterprise execution, servers offload the heavy cryptographic lifting to rack-mounted hardware security modules, built to process thousands of requests per second while physically isolating the keys from the main operating system. Once deployed, keys must be actively managed. Organizations employ strict key rotation to limit the exposure window if a compromise occurs, a principle known as perfect forward secrecy. If a device is stolen, the key is immediately invalidated globally using the online certificate status protocol. Finally, at the end of their life cycle, keys must be destroyed. Through a process called cryptoshredding, the precise keys used to encrypt a specific dataset are deleted. The ciphertext remains, but without the key, the underlying data is permanently rendered inaccessible, bypassing the need to wipe thousands of physical storage drives. The mathematical perfection of an AES-256 cipher is functionally irrelevant if the key is generated poorly, stored in plaintext, or attached to a fake identity. Trust requires both the logic of the algorithm and the physical isolation of the hardware. We have a working architectural ecosystem. Hardware security modules generate the keys. The public key infrastructure verifies the identities. Asymmetric math negotiates the connection, and hardware-accelerated symmetric math processes the bulk data. However, this equilibrium relies on the continued difficulty of specific mathematical problems. A massive shift in computational power is approaching that targets the very logic of our current trapdoor functions. The fundamental problem lies in the trapdoors. A sufficiently stable quantum computer running Shor's algorithm will be able to solve both prime factorization and discrete logarithms with extreme efficiency. When that threshold is crossed, every RSA and ECC implementation in existence will become obsolete. To maintain security in this environment, architects are transitioning toward post-quantum cryptography. This involves adopting new mathematical frameworks, such as lattice-based or hash-based algorithms, which are believed to be resistant to quantum decryption. Cryptographic architecture requires a constant iteration of its underlying primitives. Establishing trust across a perimeterless world depends on infrastructure that stays ahead of the computational ability to break.
Welcome to this explainer. Look, we're about to unpack a massive paradigm shift in security engineering. For literally decades, we all got really comfortable relying on that classic castle and moat strategy. You know the one. But the sheer explosion of cloud computing, it didn't just breach those walls, it completely vaporized them. It forced us to build this dynamic, entirely borderless future we're living in today. All right, here's our roadmap for today. We'll hit the death of perimeters, abstracting the physical world, sharing cloud security responsibilities, entering zero-trust architecture, brains, gatekeepers, and intermediaries, and finally, calculating risks and future trends. Let's get right into it. Section 1. The death of perimeters. Assume breach. Never trust, always verify. Wow, it's kind of chilling when you really think about it, right? But it completely shatters the illusion of that old safe perimeter. With remote work and decentralized apps everywhere, attackers aren't just politely knocking at the outer gate anymore. No, you have to operate under the terrifying assumption that they are literally already sitting on the couch inside your living room. Implicit trust? Yeah, that's effectively dead. Historically, our baseline was relying on a core, trusted computing base with a reference monitor mediating all the access. And honestly, it was a really neat, elegant concept back in the day, this tamper-proof, abstract machine verifying absolutely everything. But here's the catch, and it's a big one. It actually had to be small enough to verify. As our systems just exploded in complexity, trying to maintain that tiny, secure kernel became mathematically and operationally impossible. We basically just outgrew our own defenses. Moving on to Section 2, Abstracting the Physical World. So, the NIST framework outlines 5 distinct characteristics of the cloud, from on-demand self-service all the way to rapid elasticity. And sure, they are absolutely phenomenal for scaling up a business, but they inherently multiply our attack surface. Just think about it for a second. When you pool multi-tenant resources together, a single failure in logical isolation suddenly risks massive cross-tenant data leakage. The very things that make the cloud so incredibly powerful are exactly what make it wildly dangerous if we leave them unchecked. Virtualization fundamentally changed the whole game. We stopped actually touching physical hardware and started managing purely logical targets. And because we no longer have physical access to our own servers, our entire defense strategy now rests entirely on logical controls and the APIs provided by our cloud hosts. It is a massive leap of faith. We went from physically locking a heavy server room door to basically just hoping our API keys aren't accidentally sitting exposed on GitHub. Section 3. Sharing cloud security responsibilities. Now, navigating the whole alphabet soup of IaaS, PaaS, and SaaS reveals exactly how responsibility actually shifts. In infrastructure as a service, the provider handles the bare metal, sure, but you're still stuck patching the OS. Move over to software as a service, and they take on the application itself. But, and this is a really critical insight, across every single model, securing data and identity always remains squarely on your shoulders. You never, ever get to pass that buck. It really boils down to this vital distinction. You can delegate technical responsibility, sure, but you can never delegate accountability. The cloud provider manages the security of the cloud, but you own the security in the cloud. If you accidentally leave a storage bucket public, triggering the sheer terror we saw in the disastrous Capital One breach, for example, it is legally your throat to choke. The regulators, they do not care about your provider's SLA. They only care about your misconfiguration. Which brings us to Section 4, enter Zero Trust Architecture. But before we can even establish zero trust, we absolutely have to confront the ghost in the machine. Yup, shadow IT. We all know the persistent headache of employees quietly spinning up unauthorized cloud apps just to, work faster. But it completely bypasses IT, creating massive, invisible blind spots across your entire ecosystem. You can't secure what you can't see, and shadow IT is basically the ultimate invisibility cloak for enterprise data. So to wrangle all that decentralized chaos, we deploy a Cloud Access Security Broker, or CASB. It sits right in the middle as a crucial intermediary. It actually auto-discovers those shadow services your teams thought they were hiding so well, and it enforces data loss prevention policies. This ensures your most sensitive IP doesn't quietly leak out to some unapproved server just because someone really wanted to use a shiny new productivity app. Once we finally get that visibility restored, we apply the 7 tenets of zero trust as defined by NIST. I like to think of these as the new laws of gravity for your network. Trust is never persistent. Access is granted strictly on a per-session basis, and it's evaluated against dynamic telemetry, like device posture or even geographic location. It's this exhausting, continuous loop of context-aware threat assessment that literally never sleeps. And the ultimate goal with all of this? Microsegmentation. By carving the network up into tiny, logically isolated vaults, an attacker who compromises one single user cannot move laterally. They just hit a brick wall immediately. We stop them dead in their tracks, effectively neutralizing the blast radius of a breach. It's like the digital equivalent of bulkheads on a submarine. One flooded compartment doesn't sink the whole ship. Section 5. Brains, gatekeepers, and intermediaries. Let's trace the split-second anatomy of a real access request. First, information points feed real-time threat context to the brain, the policy decision point. Its engine calculates a trust score right there on the fly. If it passes, the policy administrator sends the command down to the policy enforcement point, which is the actual gatekeeper that permits or denies access. It's a beautifully elegant, automated loop, and it's executing millions of times a day to keep unauthorized users out. All right, Section 6, calculating risks and future trends. Look, zero trust isn't cheap to build, so we have to justify the spend, right? We start with the single loss expectancy formula. By taking the total value of an asset and multiplying it by its exposure factor, security engineers can finally put a concrete and usually terrifying dollar amount on a single data breach. It totally transforms abstract cyber anxiety into hard, actionable financial data. Then we take that single loss expectation and we multiply it by the annual rate of occurrence. This gives us the annual loss expectation. And guys, this is the exact math you slide across the boardroom table to business leaders to prove that funding cloud controls is drastically cheaper than rolling the dice on a catastrophic breach. It completely shifts the conversation, making security an investment in risk reduction rather than just an annoying IT expense. Looking ahead, defense is getting incredibly proactive. We're shifting left with infrastructure as code, actually defining our security configurations directly in the pipeline, so we catch misconfigurations before a resource is even born. And if you pair that with AI, we are now automating dynamic trust decisions in milliseconds, completely removing the human bottleneck. The whole future of security is code that defends itself before it's even fully deployed. I want to leave you with this final thought. The perimeter is gone. Poof! And the attack surface, it is only expanding. As IoT and AI completely blur the lines between operational technology on a factory floor and the smart devices sitting right there in your living room, our physical and digital worlds are permanently merging. So you have to ask yourself, what implicit trust are you still blindly handing out in your own architecture? Thanks so much for joining me for this explainer. Stay curious and stay secure.
For decades, information security relied on a simple analogy, the castle and the moat. Organizations built thick perimeter firewalls and assumed everything inside was safe. But when you retrofit defenses, an attacker only needs one flaw to breach the wall. Once inside, that bolt-on security evaporates. This strategy failed because it was entirely predicated on the concept of a trusted internal network. Access was granted based on location or IP address. Today, with distributed workforces and cloud computing, that static, location-based perimeter no longer exists. In its place is the zero trust architecture. Zero trust operates on the premise that an organization should not automatically trust any request, regardless of whether it originates inside or outside the network. It replaces network-centric assumptions with a model focused entirely on user identity and data protection. The architecture shifts from static perimeter rules to dynamic enforcement. Every interaction requires continuous, context-aware policy decisions and identity verification, reducing the blast radius of a compromise. But qualitative guidelines alone aren't enough. To guarantee security, the architecture requires mathematical proof. We achieve this by defining the computer system as a state machine. Every time a user reads a file or writes to a database, the system transitions from one state to another. If we can apply strict logical access control models to govern every single transition, we can mathematically prove the system will always remain in a secure state. Achieving true enterprise resilience requires embracing deterministic mathematical access control rules and integrating them into the very inception of the system's design. To understand how these rules work, we have to look at the specific goals of the architecture. For military and intelligence systems, the absolute priority is confidentiality. Information must be kept secret. In the 1970s, the United States Department of Defense needed a way to mathematically guarantee this secrecy across shared computer mainframes. They developed the Bell-LaPadula access control model. This diagram visualizes Bell-LaPadula as a multi-level security system. It organizes both the subjects, the users or processes, and the objects, the files and data, into a strict vertical hierarchy of classification. The model enforces confidentiality through two primary rules. First, no read up. A secret subject is permitted to read an unclassified object. However, attempting to read top-secret data is prohibited. You cannot pull data from a level higher than your clearance. The second rule is the star security property, no write down. This prevents data leakage. A user on a secret project can write up into a top-secret file, but attempting to save that classified information into an unclassified document is mathematically blocked. To ensure these mathematical proofs hold over time, the model relies on the tranquility principle. This rule dictates that the security levels of subjects and objects cannot change while the system is actively operating, locking the verifiable state in place. Bell-LaPadula perfectly guarantees secrecy. By forcing a one-way upward flow of information, reading down and writing up, data can never leak out of the system. But this model has a critical blind spot. It completely ignores the accuracy of the information being written. In commercial banking, healthcare, and industrial control systems, secrecy is secondary. A hospital does not care if a blood type is kept secret from the staff. It cares that the blood type recorded is absolutely accurate. The priority is integrity. To protect data from corruption, systems rely on the BIBA integrity model. Mathematically, it is the exact logical inverse of Bell-LaPadula. This diagram compares them. Bell-LaPadula tiers by secrecy, BIBA by integrity. BIBA's no read down prevents high-tier systems from ingesting unverified data. Its no write up explicitly blocks low-trust users from modifying high-trust databases. Ultimately, secrecy flows up, while integrity flows strictly down. The BIBA model proves that achieving perfect accuracy requires a policy of read up, write down. For an architecture attempting to provide both secrecy and accuracy, the requirements of one model directly obstruct the rules of the other. The rigid hierarchies of BIBA are effective for strict academic models, but they are difficult to implement in the messy, dynamic environment of modern commerce. In 1987, the Clark-Wilson model solved this by taking a different approach. Instead of using lattice levels, it protects integrity by enforcing well-formed transactions. Clark-Wilson forbids subjects from directly accessing critical data assets, called constrained data items. Instead, all access is routed through a certified program known as a transformation procedure. This creates a mandatory pathway, subject to program to object, known as the access control triple. Systems must accept external, unvalidated inputs, classified as unconstrained data items. When an unconstrained item enters, the transformation procedure validates the input, applies business logic, and formally converts it into a trusted constrained data item. To maintain this rigid structure, strict enforcement rules apply. Only certified transformation procedures are permitted to alter the data. Furthermore, users must be explicitly authorized to execute specific procedures, guaranteeing a separation of duties. Clark-Wilson achieves a provably secure state by removing direct human interaction from the database. Every single modification must pass through a certified software pathway. But mathematical models are just blueprints. A theoretical rule against writing down or reading up is useless unless a physical mechanism forces the system components to obey. This boundary represents the reference monitor. It is the absolute, unavoidable mediator of all access between subjects and objects within an operating system. To function correctly, the implementation of this monitor, the security kernel, must meet 3 criteria. It must be tamper-proof. It must be invoked on every single access request without exception, and it must be small. That final requirement, keeping the kernel small and simple, maps directly to the security design principle known as the economy of mechanism. Complexity breeds vulnerability. If a security mechanism is too large, it is impossible to rigorously test and mathematically verify its logic. An unverified kernel undermines the entire access control model it is supposed to enforce. We also have to account for what happens when a mechanism fails. A fail-secure architecture prioritizes the protection of the asset. If an error occurs, the system defaults to a state that denies access. A fail-safe architecture prioritizes human life, defaulting to an open, unlocked state during an emergency. You can design a flawless mathematical access policy, but if the reference monitor executing it is too complex, or if it fails into a vulnerable state, the entire structural integrity of the system collapses. It is easy to look at the terminology of the 1970s and dismiss these models as historical artifacts.
But these abstract theories are the active blueprints running modern enterprise infrastructure today. This split-screen diagram maps the theory to the practice. In the first panel, the strict confidentiality of Bell LaPadula directly mirrors the multi-tenancy isolation of cloud providers, mathematically enforcing that data from one corporate tenant is never visible to another. In the second panel, the Biba integrity model provides the exact logic for modern secure boot processes, preventing low-integrity, unsigned code from executing at the operating system level. And in the third panel, the Clark-Wilson access control triple maps perfectly to modern API gateways. Users interact with cloud databases exclusively through API endpoints that validate input and enforce business rules. Enterprise security rests on mathematically proven state transitions, guaranteed by the architecture rather than individual software products. In the era of zero trust, the assumption of safety is gone. You cannot evaluate a network's structural resilience without understanding the deterministic logic governing its data. As the external perimeter continues to dissolve, formal access control models and secure design principles serve as the final, most reliable layer of defense for systems engineers.
Welcome to this explainer on advanced security architecture. Today, we're totally demystifying how a truly secure system is built. We're going to explore how we construct an impenetrable digital fortress, literally starting from the physical hardware bedrock all the way up to the high walls of software memory isolation. Here's the architectural blueprint for our explainer today. We'll be covering 1. The physical root of trust. 2. Securing the endpoint with TPMs. 3. Enterprise cryptography with HSMs. 4. Software isolation in rings. 5. Defeating exploits with ASLR and DEP. And 6. Containment and the power of sandboxing. Let's jump right in. So let's kick things off by confronting what I like to call the ultimate paradox of cybersecurity. Think about it. If an environment is already compromised, how can the software running on it reliably tell you it's safe? I mean, if a malicious actor has already subverted the operating system, the exact tools you're using to check for malware might just be lying right to your face. Section 1. The physical root of trust. That paradox we just talked about perfectly sets up this core concept. The harsh reality here? Software just can't verify itself. We absolutely have to establish our digital fortress on a foundation that malicious code simply cannot alter or trick. We establish this through what's known as a root of trust. Now, the key phrase here is burned into the silicon. We're moving completely away from reactive software protections and stepping into proactive hardware-rooted assurance. This is a dedicated hardware component that's physically isolated from your main system memory. Because its logic is literally manufactured right into the physical chip, it gives us an unforgeable identity. It creates this highly secure environment where cryptographic keys are totally safe from being intercepted by any sneaky memory scraping malware.
Section 2. Securing the endpoint with TPMs. Let's look at how this builds into practical application by zooming in on the specific hardware vault installed on your individual laptop or workstation.
This specialized microcontroller is your Trusted Platform Module, or TPM. You know when you press the power button on your computer? Right then, the TPM executes a measured boot. It calculates a cryptographic hash of every single boot component, the BIOS, the firmware, the bootloader, and extends it into platform configuration registers using a one-way mathematical function. Basically, it creates a cumulative, ordered digest of all the software that just executed. If a rootkit or unauthorized firmware tries to load, the math completely changes. The baseline fails, and the system instantly knows its integrity is compromised, stopping that stealthy malware dead in its tracks before your OS even finishes waking up.
Think of the TPM as a personal safe bolted right to the floor of your computer, using two really powerful capabilities. First up is binding. This encrypts data with a key that is permanently unique to that exact TPM. This means someone can't just rip out your hard drive and plug it into another machine to read your data. No way. Second is sealing, which ties the release of those cryptographic keys to the specific PCR hash values we just talked about. The TPM is incredibly stubborn. It will only unseal those keys if the system boots into a known, perfectly trusted configuration.
Section 3. Enterprise cryptography with HSMs. Now, let's scale this up a bit. What if you're a major financial institution, or maybe you're managing the public key infrastructure for a massive global corporation? You need to secure thousands of transactions a second, not just one local hard drive.
In that kind of high-stakes scenario, you upgrade from a personal safe to a full-blown enterprise bank vault. You move from a TPM to a hardware security module, or HSM. While the TPM is a relatively low-cost chip sitting on your motherboard, the HSM is a centralized, high-performance physical appliance directly attached to your network. These things are engineered to extremely strict FIPS standards, complete with tamper-evident casings, light sensors, and voltage monitors. If someone actually attempts to physically breach an HSM, it triggers an immediate zeroization. It literally and cryptographically wipes out all the keys inside to prevent theft. It is the absolute ultimate defense for an organization's core cryptographic infrastructure. Section 4. Software isolation and rings. So, having laid out this impenetrable, immutable hardware bedrock, we can now confidently move up into the operating system itself to establish our internal VIP clearance levels. To enforce the principle of least privilege, operating systems rely on the CPU protection ring model. It's essentially a hardware-enforced hierarchy of privilege. Down at the very core, in Ring 0, we have kernel mode. This is the ultimate VIP section, the core operating system with direct, totally unrestricted access to physical memory and hardware. Out on the edge, in Ring 3, is user mode. This is where your web browsers, office suites, and games hang out. Applications out in Ring 3 cannot directly interact with the hardware. They literally have to politely ask the kernel in Ring 0 to do it for them. This strict isolation is a game changer. It ensures that a vulnerability in a standard user app can't bring down the whole system. It's exactly why a glitchy video game might crash to your desktop, but it definitely won't take down your entire computer's OS along with it.
Section 5. Defeating exploits with ASLR and DEP. But here's the thing. Attackers are incredibly clever. Even trapped within those outer user rings, they're going to try to map out an application's memory to launch nasty attacks like buffer overflows, injecting their own malicious shellcode. So our fortress needs active booby traps.
First up in our tag team of active defenses is ASLR. Buffer overflow attacks rely entirely on predictability, right? The attacker needs to know exactly where a specific piece of code lives in memory so they can hijack it. ASLR completely ruins this by acting like a high-speed shell game. Every single time an application runs or the system reboots, ASLR randomly rearranges the positions of key data areas in memory. Because the locations are constantly shifting around, an exploit that works perfectly on one machine is just going to completely crash on another simply because those hard-coded memory addresses are no longer valid. But ASLR's shell game relies entirely on entropy, or randomness. On older 32-bit systems, the memory address space was actually so small that an attacker could literally brute force the ASLR. They'd just repeatedly guess until they hit the right address, sometimes in a matter of seconds. But when you look at the 64-bit architecture, it's a completely different story. The massive jump to roughly 18 exabytes of memory creates millions of potential values.
It makes brute forcing these randomized addresses computationally infeasible. No way they're guessing that.
Okay, but what if the attacker gets unbelievably lucky and actually finds where ASLR hid the memory? That's exactly where ASLR's partner, DEP, steps in. If ASLR hides the treasure, DEP neutralizes the attacker's weapons. Data execution prevention uses a physical feature on the CPU called the no execute, or NX bit. It explicitly marks certain areas of memory, like the stack and the heap where data is normally stored, as strictly non-executive. So even if an attacker successfully manages to inject malicious code into a data buffer, the split second the CPU tries to run it, the hardware detects the NX bit, throws an exception, and instantly terminates the process. Game over.
Section 6, Containment and the Power of Sandboxing. We've arrived at the final layer of our defense. What's our strategy of last resort when an incredibly complex, highly untrusted application, say a web browser processing code from an unknown website, is targeted?
We drop it straight into the sandbox. Sandboxing isn't just about protecting one process from another. It is about protecting the entire system from one specific, highly risky process. It's a comprehensive quarantine zone. The sandbox creates a temporary, virtualized file system, often called a truth jail, so any changes the malware makes are just instantly discarded the moment the process ends. It isolates the network, totally cutting off outward communication to the attacker's command and control servers. Plus, it uses API hooking to strictly monitor behavior, blocking any attempt to tweak system registry keys or inject code elsewhere. This is exactly how enterprise email security gateways can safely detonate those highly suspicious attachments without risking the entire company network.
And this all brings us to the ultimate architecture of resilience. When we combine everything we've just covered, it creates a defense that's vastly more effective than the sum of its individual parts. From the immutable bedrock of the TPM vault verifying the OS kernel, moving up through the CPU protection rings, hitting the memory booby traps of ASLR and DEP, and going all the way to the dynamic software quarantine of the sandbox. These layered defenses work seamlessly together. They form a transitive chain of trust that's specifically designed to mitigate the incredibly advanced, fileless, memory-only threat vectors we're dealing with today.
I'm going to leave you with this final provocative thought to consider. Our entire modern security architecture, especially as we lean harder into zero-trust models, places absolute fundamental faith in this hardware bedrock. Every single software defense out there assumes the silicon is uncompromised. So I have to ask you, what happens to our entire zero-trust fortress if that fundamental physical hardware bedrock is ever truly broken? It's something every security architect really needs to deeply consider. Thanks for joining me for this explainer, and keep building those fortresses.